Now we can talk about quadrilaterals. A shape with 4 line segment sides is a quadrilateral. So here we have 4 random quadrilaterals. These are actually called irregular quadrilaterals. It is possible for a quadrilateral like these to have 4 completely different side lengths and 4 completely different angles. And sometimes the test will ask about an irregular quadrilateral. The test is more likely to ask about the very symmetrical quadrilaterals, and we'll talk about those also in this video. So of course those were the irregular quadrilaterals. The set of quadrilaterals also contains some elite symmetrical members: the trapezoid, the parallelogram, the rectangle, the rhombus, and the most elite of all, the square. And this deserves a comment. We'll talk about this again when we get to squares. But the funny thing about a square is, if you think about it, it's one of the first shapes you learn when you're a little kid, so it's a very familiar shape. And the fact that it's so familiar makes it hard to appreciate how special and how elite a shape it is. It's very hard to prove something is a square. A square is an incredibly elite shape. And we'll talk about this more when we get to it. First of all, let's talk about what's true for all quadrilaterals, absolutely every member of the set. For every quadrilateral, the sum of the 4 interior angles is 360 degrees. That you need to know. One way to understand this is to see that every quadrilateral can be divided into 2 triangles. So here we have a random quadrilateral, and we draw the line from B to D, and we can see we have 2 triangles. In triangle ABD, we have the 3 blue angles. They have to add up to 180. In triangle BCD, we have the 3 red angles. Those have to add up to 180. And really, the angles in the whole quadrilateral, ABCD, that's just the sum of the red angles plus the blue angles. So red plus blue has to equal 180 plus 180. That's 360. So that's why every quadrilateral has a sum of angles of 360. Now this line that we drew from one vertex to the opposite vertex is called a diagonal. Triangles don't have diagonals, but every quadrilateral has exactly 2 diagonals. So here's a quadrilateral with its 2 diagonals drawn. Segments EG and FG are the diagonals of quadrilateral EFGH. As we will see, some quadrilaterals have diagonals with special properties. Now we can start talking about the special quadrilaterals, the more elite quadrilaterals that are more common on the test. The parallelogram. All parallelograms have the following 4 properties. Property number 1, opposite sides are parallel. This is kind of the definition of a parallelogram. So AB is parallel to CD, and AD is parallel to BC. Property number 2, opposite sides are equal. So AB equals CD, and BC equals AD. Property number 3, the opposite angles are equal. So the red angles are equal, and the blue angles are equal. And property number 4, the diagonals bisect each other. So their point of intersection M is actually the midpoint of each diagonal. And so we could say that AM equals MC, and separately BM equals MD. So those 4 properties are really important. I will refer to those as the big 4 parallelogram properties. And here's the interesting thing. They always come together. They always come as a package deal. That is, if any one of them is true, it automatically means that the other 3 have to be true. And if any one of them is not true, it automatically makes the other 3 not true. So it is absolutely impossible to construct a quadrilateral that has some of the big 4, but not others. Either a quadrilateral has to have all 4 of them, or has none of the 4 of them. And that's why they're so important. And any quadrilateral that has all 4 of these true is a parallelogram. Again, these 4 properties are parallel opposite sides, equal opposite angles, and diagonals bisect each other. So any one of those automatically makes the other 3 true. Now we can talk about rhombuses. Rhombuses are equilateral quadrilaterals. That is, a quadrilateral with 4 equal sides. Some people think about this as a diamond shape, especially if we orient it this way, if we orient it with the 4 points pointing horizontally and vertically. Diamond is just kind of a casual or colloquial way to refer to a rhombus. So rhombuses are parallelograms, so they automatically have the big 4 properties. Every rhombus has those big 4 properties true that we just talked about. In addition, there are 2 special rhombus properties. All 4 sides are equal, and the diagonals are perpendicular. So if you have a parallelogram with perpendicular diagonals, it has to be a rhombus. I will point out, though, it is possible to have an irregular quadrilateral that has perpendicular diagonals. That diagonal property is separable from the others. So you could have an irregular quadrilateral that doesn't have the big 4, doesn't have equal sides, but it does have perpendicular diagonals. That property alone can be separated from the other 4. It's not like the big 4 properties that always come together. Rectangles. Rectangles are quadrilaterals with 4 90-degree angles. We could call them equiangular quadrilaterals. It's very interesting. With a triangle, the only equilateral triangle is equiangular, and the only equiangular triangle is equilateral. Those two always have to come together with triangles, but we can separate those two once we get to quadrilaterals or to any higher polygons, that you can have the equiangular shape without the equilateral shape. So rectangles have all equal angles. And in fact, one of those rectangles, EFGH, is a golden rectangle. Rectangles are parallelograms, and the big 4 parallelogram properties are true for them. In addition, there are 2 special rectangle properties. Obviously, all 4 angles are equal to each other, and the diagonals are congruent. So QS equals PR. And again, this diagonal property, this can be separated out from the others. We could have an irregular quadrilateral that doesn't have any of the big 4, doesn't have right angles, but it does have congruent diagonals. So that property can be separated out from the other 4. It's important to appreciate that. Finally, among this set, we'll talk about squares. Squares are the most elite quadrilaterals, the shape with the highest number of special properties. A square is a rectangle, a square is a rhombus, and a square is a parallelogram. So it has all the rectangle properties, all the parallelogram properties, all the rhombus properties. And so it's a very, very special shape. If we are told that a figure is a square, now that's amazing. If the test problem actually says this shape is a square, they're giving us a ton of information. And that is a really powerful thing to know. There's all kinds of geometry facts we know if we simply have the information that a shape is a square. But it's very hard to prove that something is a square. Don't be gullible in assuming that a shape is a square when you don't have sufficient information to do so. That is one very common trap on the test. If the shape is close to being a square but not exactly a square, it doesn't necessarily have any of the square properties. So here are 2 drawn to scale diagrams. Both of these look like squares, but neither is. So the one on the left, EFGH, turns out to be a rhombus, but it has one angle, so the 4 sides are equal, but one angle is slightly less than 90 degrees, the other angle would be slightly more than 90 degrees, so it's not exactly a square. The other one has 3 equal sides, and that has one side that's a little bit less. KL is a little bit less. It looks like angle M is 90 degrees, but angle K is greater than 90 degrees, and the other 2 are slightly less and unequal to each other. So that's a totally irregular quadrilateral, but drawn to scale, it looks like a square. So just the fact that even if we have something that is drawn to scale and looks like a square, there's no guarantee that it is a square. Here's a practice problem. Pause the video and then we'll talk about this. Okay, this is a very odd question format. Can we determine that ABCD is a square if we know either of these? So BC equals CD and angle B is 90 degrees. So that's fact number 1. AD equals AB and angle D equals 90 degrees. And so the question is, using just one of them, can we determine that it's a square? If we put both of them together, is that enough to determine that it's a square? Or even if we put them both together, it's not enough to prove that something is a square. Turns out that if even both facts together are true, that does not guarantee that the shape is a square. It could be just two congruent right triangles attached at the hypotenuse, like this. So in this diagram, it is true that BC equals CD. It is true that AD equals AB, and we do have right angles at B and D, and yet ABCD is not a square. In fact, it's not any special quadrilateral at all. All this information is not enough to determine that ABCD is a square, and the answer to the question is C. Now we can talk about trapezoids. A trapezoid has exactly one pair of parallel sides. So these are trapezoids. It is possible for a trapezoid to have two right angles in it on one of the legs. The two parallel sides are called bases, and the non-parallel sides are called legs. The two angles on a leg are always supplementary. So if one of them is 90 degrees, the other has to be 90 degrees. It's always true that, for example, A plus B equals 180 and C plus D equals 180. And that's because of the basic properties of parallel lines. Some trapezoids have two equal legs. We call these symmetrical trapezoids, or sometimes a more formal name for them is isosceles trapezoids. Either term is fine. If the two sides are parallel, and if KJ equals LM, the legs are equal, then we know that the angles on the opposite sides have to be equal. Essentially, the shape becomes entirely symmetrical. So angle K equals angle L, angle J equals angle M, and also the diagonals have equal length. Here's a practice problem. Pause the video and then we'll talk about this. Okay, ABCD is a trapezoid with length shown. Find the diagonal AC. Well, there's no direct formula. There's no way we could just plug in the four numbers we have and find the diagonal. We're going to have to find this step by step. Essentially, we're going to be working our way up to the Pythagorean theorem. As a general rule, in any geometry problem where you're asked to find the length of a slanted line, chances are very, very good that the Pythagorean theorem is hidden somewhere in that problem. And your job is to just figure out how to use the Pythagorean theorem. That's a really big idea. So here what we're going to do is we're going to draw perpendicular segments from BC down to the base. So what we create, we have some kind of rectangle in the middle. It looks like it might be close to a square, but it's not exactly a square. And then we have two symmetrical right triangles on each side. So we know that the opposite side from BC, EF, that also has to be 11. Well, that whole base is 21. And we know that AE and FD, the two small sides of the triangle, those have to be equal to each other because those triangles are congruent. So it must be true that each one has a length of 5. So we split up the area of the base, 5, 11, 5, and that adds up to 21. Well, now, notice in those right triangles, we have 5 blank 13. That should ring a bell. This is a 5, 12, 13 triangle, so it must be true that BE and CF equal 12. So now we know the length of the height. Now we can think about that diagonal. That diagonal AC is the hypotenuse of right triangle ACF. And we know that AF is 5 plus 11, 16, and CF is 12. Well, this is the 3, 4, 5 triangle scaled up by a factor of 4. It's a 12, 16, 20 triangle. So the hypotenuse AC is 20. That's the length of the diagonal. So again, notice that we found everything using the Pythagorean theorem. And once again, whenever you have to find the length of a diagonal, or really the length of almost any slanted line, chances are very, very good that it's a Pythagorean theorem problem. This diagram shows the conceptual relationship among the quadrilaterals. So, first of all, there are many quadrilaterals that are neither parallelograms or trapezoids. So those are just the irregular quadrilaterals that are outside the two big circles. Inside the parallelogram circle, everything in that circle has the big four parallelogram properties. And nothing outside the parallelogram circle can have any of those properties. Inside the parallelogram circle, we have rhombuses, rectangles, and then squares are the intersection of rhombuses and rectangles, because squares are both rectangles and rhombuses. And of course, they're parallelograms also. Separately, we have the trapezoids. Within the trapezoids, we have the region of symmetrical trapezoids, a special case. And again, the test most likes to ask about the more elite, more symmetrical and special kinds of quadrilaterals, because those have more properties. And so there's more to ask about. That's why the test likes them. In summary, it's true for all quadrilaterals that the sum of the angles is 360 degrees. It's very important to know the big four parallelogram properties: parallel opposite sides, equal opposite angles, and diagonals bisect each other. Those four always come together. So you can't have any shape that has some of those true and others of them not true. They're either all four of them true or all four of them false about a particular shape. A rhombus has four equal sides plus the big four. It also has perpendicular diagonals. Rectangle has 90-degree angles plus the big four. It also has congruent diagonals. A square is a rectangle and a rhombus, so a square has all the rectangle properties, all the rhombus properties, and all the parallelogram properties. A trapezoid has exactly one pair of parallel sides, and a symmetrical trapezoid, or an isosceles trapezoid, has equal lengths. This means it has equal angles on each side as well as equal diagonals. Now we can talk about areas of quadrilaterals. In this video, we'll review how to find the area of the special quadrilaterals. So first of all, the most special quadrilateral is a square. If a square has a side of S, then the area is simply S squared. In fact, even in algebra, raising a number to the second power is called squaring, precisely because this is the way to find the area of a square. So the word we use in algebra actually comes from the basic geometric fact. For the other special quadrilaterals, the general formula is area equals base times height, but we need to think carefully about this. The formula area equals base times height most obviously works for a rectangle, in which B and H are sides of the rectangle. As with triangles, remember that the base needs not be horizontal. Any side can be the base, and the height must be perpendicular to it. So for a rectangle, the area is just the product of the two different side lengths. The area A equals B times A also works for rhombuses and parallelograms, and any side can be a base, but the height has to be perpendicular to the base. So the height will not lie along a side. Instead, the height will be what's called an altitude, a line perpendicular to the base. And so we need to find that height. The length of the altitude is not given, then almost always one can find it from the Pythagorean theorem. So here's a practice problem. Pause the video and then we'll talk about this. Okay, so if Jn equals 1 and Nm equals 2, then all the way across from J to M has to be 3. And because it's a rhombus, every side has to have a length of 3. So now look at the right triangle JKN, in which JK, the side of the rhombus, is 3, and Jn we're given as 1. Well, we use the Pythagorean theorem in that triangle to find Kn. Kn squared equals Jk minus Jn squared. 3 squared is 9, so 9 minus 1 is 8. Means that kn is the square root of 8. Of course, we can simplify that down to 2 root 2. And that is the height of the rhombus. So now we're ready to apply area equals base times height. We know that the base is 3 and the height is 2 root 2. And we can simply multiply these and get 6 root 2. If these operations with roots are a little bit unfamiliar, I would suggest going back to the Power and Roots module and watching the video, Operations with Roots. With trapezoids, we have to rethink a bit because there are 2 bases, 2 parallel sides. So what exactly would we mean by base times height? Well, the height is pretty clear, but we have 2 bases, so what are we going to do? One way to find the area is to find the average of the bases and multiply this by the height. So that is the formula. If we average the bases and multiply the height times the average of the bases. Sometimes we can find the area of a trapezoid by subdividing the trapezoid into a central rectangle and 2 side right triangles. So this is often what the test will have us do. We have 2 side right triangles. We can find information about those with the Pythagorean theorem, and that will allow us to solve for everything and find all the areas. And of course, if it's a symmetrical trapezoid, those 2 side right triangles will be congruent, which makes things even easier. Here's a practice problem. Pause the video, and then we'll talk about this. In trapezoid ABCD, altitudes are drawn. If AF equals 5, find the area of the trapezoid. Well, first of all, we're going to look at ABF. That little triangle, we have a leg of 5, an unknown leg, and a hypotenuse of 13. So, of course, that's a 5, 12, 13 triangle, and BF equals 12. So we can find that just from knowledge of our Pythagorean triplet. We don't even need to do a calculation. So BF equals 12, that means that CE also equals 12. So we can find the area of the triangle ABF, and that has to be 1/2 5 times 12, 1/2 6, 5 times 6 is 30. We can also find the area of the rectangle. 10 times 12 is 120. Now that triangle on the left, triangle CED, that's going to be blank 12, 15. Well, of course, that's a 3, 4, 5 triangle multiplied by 3, so that's going to be 9, 12, 15. And then the area, 1/2 9 times 12, well, that's 9 times 6, which is 54. So the whole area is going to be triangle plus rectangle plus triangle, 30 plus 120 plus 54, and that equals 204. In summary, a square has an area of s squared. The rectangle, rhombus, and parallelogram have an area of base times height. We have to be careful in a rhombus or a parallelogram. Any side can be the base, but the other side is not going to be the height. The height has to be perpendicular to the base. We need to find the altitude. A trapezoid is the average of the bases times the height. And for any slanty shapes, think about subdividing into rectangles and right triangles. And this might even be true, for example, if we were dealing with an irregular quadrilateral. And expect to find the Pythagorean theorem involved in anything involving a slant. Polygons. In this lesson, we will expand beyond triangles and quadrilaterals to the entire realm of polygons. A polygon is any closed figure with all line segment sides. So here we have an example of a polygon with 3 sides, a triangle with 4 sides, a quadrilateral, and then one with 5 sides and 6 sides. And you could imagine it could have many, many more sides. A geometric figure is not a polygon if, first of all, the figure doesn't close. So, for example, something like this is not a polygon, has none of the polygon properties. If the sides cross, so we don't have to worry about that. The test is not going to make us think about that. And if not all the sides are straight? Well, this final one is interesting. The test could give us something that was a combination of a polygon and a circle, and of course we'd have to solve that using both polygon properties as well as circle properties. So this is not strictly a polygon either. We'd have to use circle properties as well to figure out something about the shape. The only polygons that will appear on the test are convex polygons. That is, polygons in which every single vertex points outward. A concave polygon has one or more vertex that points inward. Well, turns out those technically are true polygons, but the test is not going to ask about them, so we don't need to worry about them. So let's talk about the names of the polygons. Obviously, if a polygon has 3 sides, we call it a triangle. If it has 4 sides, we call it a quadrilateral. If it has 5 sides, we call it a pentagon. That's a term you need to know. If it has 6 sides, it's a hexagon. That's a term you need to know. 7 sides is kind of an irregularity. We don't need to, for a variety of reasons, and we'll talk about this more in the next video, we don't worry about 7-side shapes that often. They don't come up that often. But an 8-sided shape, the octagon, that's a term you need to know. What is true for all polygons? Well, first of all, any segment that connects 2 non-adjacent vertices is called a diagonal. So triangles, as we found out, don't have diagonals. Quadrilaterals have exactly 2 diagonals. Pentagons have 5 diagonals. Hexagons have 9 diagonals. For higher polygons, we could count diagonals using the techniques in the counting modules. That actually becomes a much harder problem to figure out. Say, how many diagonals does a polygon with 20 sides have? That's something we're not going to worry about right now. We're going to wait till we get to the counting problems. That's really much more a counting problem rather than a geometry problem. So don't worry about that right now. Angles in polygons. Of course, the sum of the 3 angles in a triangle is 180 degrees. The sum of the 4 angles in a quadrilateral is 360 degrees because we can divide a quadrilateral into 2 triangles along a diagonal. We can extend this pattern to higher polygons. Any pentagon can be broken into 3 triangles. So from any single vertex, we can draw 2 diagonals. That divides it into 3 triangles. And therefore, the sum of the angles in the pentagon must be the sum of the angles in 3 triangles. 3 times 180, which is 540. That's a good number to know. Any hexagon can be broken into 4 triangles. So from any vertex, we can draw 3 different diagonals, divide the shape into 4 different triangles. The sum of the angles in the hexagon must be the sum of the angles of those 4 triangles. 4 times 180 is 720. That's a good number to know also. You might see where this pattern is going. So with a quadrilateral, there are 4 sides, there are 4 vertices. From any vertex, we can draw only 1 diagonal that divides it into 2 triangles for a sum of 2 times 180, which is 360. For a pentagon, from any one vertex, we can draw 2 diagonals. That divides it into 3 triangles, so the sum of the angles is 3 times 180, which is 540. For a hexagon, from any vertex, we can draw 3 diagonals, which divides the shape into 4 triangles, and the sum of the angles is 4 times 180, which is 720. Now, where's this pattern going? If we have an n-sided quadrilateral, an n-sided polygon with n vertices, that means that we could draw from any one vertex, we could draw n minus 3 diagonals. The n minus 3 diagonals would divide the shape into n minus 2 triangles, and then the sum of the angles would simply be n minus 2 times 180, because we'd have n minus 2 triangles. So the sum of the angles in an n-sided polygon is n minus 2 times 180. That's an important formula to know, and again, I would urge you, don't simply memorize it, make sure you understand where it comes from. For example, consider an 18-sided polygon in which all the angles are equal. What does each angle equal? Pause the video and see if you can work this out for yourself. Okay, so we know that the sum of the angles must equal n minus 2 times 180, so 16 times 180. I'm not going to multiply that out, I'm just going to leave it like that, 16 times 180. And if all 18 angles are equal, then we'll divide that sum of the angles by 18 to get one of the single angles. Well, when we divide by 18, we can very easily cancel. 180 divided by 18 is just 10, and so that equals 160 degrees. And that is the measure of each one of those 18 angles. And here's the actual shape. An 18-sided polygon in which all the angles are equal. Notice that it looks awfully circle-like, and that is true of many of the higher polygons that have all equal angles and all equal sides. In summary, a 3-sided polygon is called a triangle. A 4-sided polygon is called a quadrilateral. 5-sided polygon is called a pentagon. 6-sided one is called a hexagon. 8-sided one is called an octagon. Those are words you need to know. A segment from one vertex to a non-adjacent vertex is a diagonal. And the sum of the angles in an n-sided polygon equals n minus 2 times 180. Now we can start talking about the most special and elite of all the shapes in geometry, the regular polygons. To begin, we need to discuss this very funny word, regular. In everyday life, regular means ordinary, common, not exceptional in any way. In geometry, the word regular means exactly the opposite of this. And this is what's so confusing. This is one word where the use in mathematics, the use in geometry, is the absolute opposite of its colloquial everyday use. In geometry, the word regular means special and elite. In particular, when the word regular describes a polygon, it means that the polygon must have two properties. It must be equilateral, having all equal sides, and also equiangular, having all equal angles. In any category of polygons, the regular polygon of that category is the most symmetrical and well-balanced example of that category. It's the most elite member of the category. The regular triangle is an equilateral triangle. The regular quadrilateral is the square. Equal sides, equal angles. This is the regular pentagon. Notice that the sum of the angles in any pentagon is 540 degrees, so we could find the measure of the individual angles. Each individual angle we would just divide 540 by 5, and that's 108. So 108 degrees is the angle in any regular pentagon. The regular hexagon. The sum of the angles here is 720. Well, to find the individual angles, we'll divide 720 by 6. We get 120. Now that's an interesting number because 120 is the supplement of a 60-degree angle. So that's good to know that a 60-degree angle, say a little equilateral triangle, would fit neatly into any one of those exterior angles. Now a 7-sided shape, we haven't really talked about these. So technically a 7-sided shape is called a regular heptagon. The reason that we haven't talked about this is that it turns out this shape has angles that are non-integer degrees. So the math involving this shape is kind of ugly, and as it happens, because of that, the test just never asks about it. So that's why you don't need to worry about heptagons at all. They never show up on the test. The regular octagon. Sum of the angles is 6 times 180, so that is 1080. And each one of the internal angles are equal, so each one must equal 1080 divided by 80. 1080 divided by 8. So cancel a factor of 2, that's 540 divided by 4. Cancel another factor of 2, that's 270 divided by 2. 270 divided by 2 is 135 degrees. Now that's an interesting angle because that is the supplement of a 45-degree angle. And so that's a fact that can be very useful, that the supplement of a 45-degree angle is exactly what every angle in the regular octagon equals. In similar manner, we could find the individual angles in any regular higher polygon. Because we know all the angles, we could also find angles formed by the diagonals. So this is a relatively hard problem. Pause the video and think about this a little bit, and then we'll talk about this. Okay, so what we have is a regular octagon with two diagonals drawn, and we want to find the angle formed, angle x, the angle of two of those diagonals. Well, we have to think about this step by step. First of all, because it's a regular octagon, we know every interior angle is 135 degrees. Clearly, AE, diagonal AE, divides the octagon symmetrically in half. It's a mirror line for the whole octagon. So that means it must bisect the angle at A. So HAM, that little angle, has to be the bisected 135 degrees. Well, 135 degrees divided by 2 is 67.5 degrees. So that is the angle HAM, this angle right here. So we have found that angle. Now put that aside. Now look at quadrilateral ABCH. We know that the sum of the angles in any quadrilateral is 360. We know that two of the angles, the angle at A and the angle at B, are 135 degrees. Well, if you look at that shape, we realize that is a trapezoid, and because AH equals BC, it's a symmetrical trapezoid. And in fact, because it's a trapezoid, we know that the angle at H is just going to be the supplement of the angle at A. Well, the angle at A is 135 degrees, so the angle at H is the supplement of that, which is 45 degrees. And so we have found this angle right here, MHA, that angle is 45 degrees. Well, now we're in good shape, because look at that triangle HAM. We know two of the angles in that. We have this angle and we have this angle. So we know that the sum of the three angles in that triangle is 180 degrees. We add things up. We subtract 180 minus 112.5, and we get 67.5. So it turns out that, in fact, that is a little isosceles triangle, believe it or not, because two of the angles are equal. But now that we've found angle AMH, well, the angle we're interested in is just the vertical angle of that, so it has to be equal. So that means that x equals 67.5 degrees. So that is an example of a very, very hard problem. A problem like that could appear among the hardest problems on the quant section. In summary, regular polygons have all equal sides and all equal angles. We can find the sum of the angles using the n-2 times 180 formula and divide by n to find the measure of individual angles.